Imagine standing on an endless beach, trying to count every single grain of sand stretching out before you. The task seems insurmountable, doesn't it? Yet this is precisely the challenge astronomers have faced for millennia, mapping every visible star in the vast cosmic ocean above us. This monumental endeavor, known as astrometry, represents one of humanity's oldest scientific pursuits, the quest to catalog and understand the countless celestial bodies that paint our night sky. Just as each grain of sand tells a story of geological processes spanning millions of years, each star holds secrets about our universe's history, present, and future. The journey of astrometry is a testament to human ingenuity and perseverance, a story that begins with ancient astronomers using nothing but their naked eyes and primitive tools, and culminates in sophisticated space telescopes mapping billions of stars with unprecedented precision. Think about this. When you look up at the night sky, you're seeing the same celestial tapestry that inspired countless generations before us. The same stars that guided ancient mariners across vast oceans, led nomads through deserts, and sparked the imagination of philosophers and scientists throughout history. But while our ancestors could only wonder about these distant points of light, we now possess the ability to measure their positions, distances, and movements with astounding accuracy. The evolution of astrometry mirrors humanity's technological advancement. From simple angular measurements made with handheld instruments to state-of-the-art space telescopes that can pinpoint a star's position with accuracy finer than the width of a human hair viewed from miles away, we've come an incredibly long way. This progress hasn't just improved our understanding of the cosmos, it has fundamentally changed our perception of our place in the universe. Today, we'll embark on a fascinating journey through time, exploring how we progressed from rudimentary naked-eye observations to creating the most precise stellar maps humanity has ever produced. We'll discover how each breakthrough in astrometric technology opened new windows into the cosmos, revealing secrets about our galaxy's structure, evolution, and our own cosmic neighborhood. As we prepare to delve into this remarkable story, we invite you to join us on this journey of discovery. From the ancient Greeks to modern space telescopes, from counting hundreds of stars to mapping billions, this is the story of humanity's quest to chart the heavens. This is the story of astrometry. In the misty depths of the 2nd century BCE, on the small Greek island of Rhodes, a revolutionary breakthrough in astronomical science was taking shape. Hipparchus of Nicaea, often hailed as the father of observational astronomy, undertook what would become one of history's most influential scientific endeavors. Armed with nothing more than his keen eyes, a profound understanding of geometry, and rudimentary instruments like the astrolabe and armillary sphere, Hipparchus achieved what many thought impossible: the creation of the world's first systematic star catalog. This groundbreaking achievement wasn't merely a matter of counting stars. Hipparchus meticulously recorded the positions of 850 stars, categorizing them by their brightness into 6 distinct magnitude classes. Using a complex system of coordinates based on celestial latitude and longitude, he mapped these celestial bodies with remarkable precision, achieving accuracy within about 1 degree, a feat that would remain unmatched for nearly 2 millennia. The significance of this accomplishment extends far beyond its scientific merit. In an age when the seas were humanity's highways and nighttime navigation was a matter of life and death, Hipparchus's star catalog became an indispensable tool for survival. Imagine setting sail across the vast Mediterranean Sea or venturing into the unknown Atlantic Ocean with no modern navigation equipment. No GPS, no magnetic compass, no radio signals, nothing but the stars above to guide your way. In these conditions, Hipparchus's catalog became a crucial reference manual for sailors and explorers. His work laid the foundation for the development of celestial navigation, a technique that would guide mariners for the next 2,000 years. By carefully documenting the position of each star and its relationship to others, Hipparchus created what was essentially the world's first celestial positioning system. Sailors could use this information to determine their latitude by measuring the height of specific stars above the horizon, allowing them to maintain their course across featureless seas. But Hipparchus's contributions went beyond just cataloging stars. He discovered the precession of the equinoxes, the slow wobble of Earth's axis that causes the positions of stars to shift gradually over centuries. This discovery demonstrated that the heavens weren't as fixed and unchanging as previously thought, challenging the prevailing philosophical views of his time. The methods Hipparchus developed for measuring and recording celestial positions became the standard for astronomical observation for centuries to come. His mathematical approach to astronomy, combining careful observation with geometric calculations, set the pattern for all future scientific astronomy. He even developed the first known trigonometric tables, which became essential tools for later astronomers. Perhaps most remarkably, Hipparchus achieved all this without the benefit of telescopes or precise timepieces. His instruments were simple by today's standards: graduated rings for measuring angles, sundials for keeping time, and sighting tubes for aligning observations. Yet through meticulous attention to detail and mathematical rigor, he created a resource that would influence navigation and astronomy for millennia to come. The legacy of Hipparchus's star catalog extended far beyond the ancient world. His work was later expanded upon by Ptolemy in the Almagest, and his basic methods of celestial observation and documentation remained fundamental to astronomy until the invention of the telescope in the 17th century. Even today, as we launch sophisticated space telescopes and measure star positions with unprecedented precision, we're following in the footsteps of this pioneering Greek astronomer who first showed us how to systematically map the heavens. The 16th century marked a pivotal moment in the history of astrometry, ushering in what we now recognize as the first true instrumental revolution in astronomical observation. At the heart of this transformation stood a Danish nobleman named Tycho Brahe, whose contributions would forever change how we measure the heavens. Picture yourself transported to the island of Hven, between Denmark and Sweden, in the year 1576. Here, rising majestically against the Nordic sky, stands Uraniborg, a castle-like observatory unlike anything the world had seen before. This wasn't just an observatory, it was a temple dedicated to the precise measurement of the cosmos. Tycho Brahe, with the support of King Frederick II of Denmark, had created the world's first research institution dedicated to systematic astronomical observation. What made Uraniborg truly revolutionary was not just its architecture, but the unprecedented array of instruments Brahe designed and installed within its walls. These weren't the small, portable instruments of previous generations. Brahe understood that size matters when it comes to precision. His massive quadrants, some reaching several meters in height, were anchored firmly to the walls and floors of the observatory. The larger the instrument, the smaller the divisions that could be marked on its scales, and consequently, the more precise the measurements. The crown jewel of his instrumental arsenal was the Great Mural Quadrant, a massive quarter circle embedded in a wall aligned precisely with the meridian. Made of solid brass and with a radius of about 2 meters, this instrument allowed Brahe to measure stellar positions with an accuracy of 1 minute of arc, approximately 1/30th the apparent diameter of the full moon. To appreciate this achievement, consider that Hipparchus, working 17 centuries earlier, could only achieve accuracy within about 1 degree, 60 times less precise than Brahe's measurements. But Brahe's genius extended beyond just building bigger instruments. He introduced numerous innovations in instrument design. His sighting devices incorporated crossing slits and pinholes for more precise alignment. He developed new methods for subdividing scales to achieve finer readings. Perhaps most importantly, he established rigorous procedures for regular calibration of his instruments, understanding that even the most precisely crafted device could drift out of alignment over time. The observatory was staffed by a team of assistants who worked in shifts, ensuring that observations could be made whenever the sky was clear. Brahe instituted a system of multiple independent observations of each celestial object, combined with careful record-keeping practices that were revolutionary for their time. He understood that accuracy came not just from precise instruments, but from methodical observation and meticulous documentation. For 20 years, Brahe and his team worked tirelessly, creating what would become the most accurate and comprehensive pre-telescopic survey of the night sky ever compiled. His star catalog contained the positions of roughly 1,000 stars, measured with unprecedented precision. His observations of planetary positions were so accurate that they later enabled Johannes Kepler to discover the laws of planetary motion, laying the groundwork for Newton's theory of universal gravitation. It's worth pausing to consider just how remarkable Brahe's achievement was. Working without telescopes, using only the naked eye and his precisely crafted instruments, he achieved observational accuracy that wouldn't be significantly surpassed until the invention of the telescope and the micrometer nearly a century later. His work demonstrates that revolutionary advances in science don't always require completely new technologies. Sometimes, they come from perfecting and systematizing existing methods to their ultimate potential. The legacy of Tycho Brahe's instrumental revolution extends far beyond his own time. His emphasis on systematic observation, precise measurement, and careful documentation set the standard for all future astronomical research. His methods demonstrated the importance of precision instrumentation in astronomy, a principle that continues to drive the development of ever more sophisticated observational tools today. And speaking of precision, here's an interesting question for you to ponder. Can you guess what was the margin of error in Hipparchus's measurements? While Brahe could achieve accuracy within 1 minute of arc, Hipparchus, working with much simpler instruments, had to contend with significantly larger uncertainties. The answer might surprise you. The invention of the telescope in the early 17th century marked a watershed moment in the history of astrometry, fundamentally transforming our ability to study and measure the cosmos. However, it wasn't until the remarkable work of Friedrich Wilhelm Bessel in 1838 that this technological breakthrough achieved its full potential in measuring the vast distances of space. Imagine the scientific world of the early 19th century, still grappling with a fundamental question that had puzzled astronomers for millennia. Just how far away are the stars? While the telescope had already revolutionized our view of the heavens, showing us countless previously invisible stars and revealing intricate details of planets, the true scale of the universe remained a mystery. Enter Friedrich Bessel, a German astronomer whose meticulous work would finally unlock this cosmic puzzle. Bessel chose to focus his attention on a rather unremarkable star known as 61 Cygni in the constellation of Cygnus. This binary star system wasn't particularly bright or notable to the naked eye, but it had one crucial characteristic that caught Bessel's attention. It showed the fastest apparent motion across the sky of any known star, suggesting it might be relatively close to Earth. Using a specialized telescope known as a heliometer at the Königsberg Observatory, Bessel embarked on a series of incredibly precise measurements spanning many months. The principle behind Bessel's measurements was elegantly simple, though fiendishly difficult to execute. Known as stellar parallax, it involved measuring the tiny apparent shift in the star's position as Earth orbited around the Sun. Think of holding your thumb at arm's length and alternately closing each eye. Your thumb appears to shift position relative to the background. The same principle applies to nearby stars, though the shift is incredibly small, less than 1 arcsecond for even the closest stars. After months of careful observation and calculation, Bessel announced his groundbreaking result. 61 Cygni lay at a distance of about 10.4 light-years from Earth. Modern measurements put it at 11.4 light-years. For the first time in human history, we had measured the distance to a star other than our Sun. The significance of this achievement cannot be overstated. It provided the first concrete proof that stars were indeed distant suns, and gave us our first true sense of the cosmic scale. This breakthrough opened the floodgates for a new era in astrometry. Other astronomers quickly followed Bessel's lead, measuring parallaxes for other nearby stars. Thomas Henderson soon measured the distance to Alpha Centauri, and Friedrich Georg Wilhelm von Struve determined the distance to Vega. Each new measurement added another piece to our understanding of the three-dimensional structure of our cosmic neighborhood. The telescopic era brought other crucial advances in astrometric precision. The invention of the filar micrometer allowed astronomers to measure tiny angular separations with unprecedented accuracy. Photography, introduced to astronomy in the mid-19th century, revolutionized star catalogs by allowing positions of thousands of stars to be recorded simultaneously and measured at leisure. The development of the transit circle, combining a telescope with precisely graduated circles for measuring angles, became a standard tool in observatory astrometry. By the late 19th century, several major observatories were engaged in massive astrometric surveys, creating ever more comprehensive and precise star catalogs. The Astronomische Gesellschaft Catalog, AGK, and the Carte du Ciel project represented ambitious attempts to map the entire sky with photographic precision. These projects, though never fully completed as originally conceived, laid the groundwork for modern astronomical databases. The telescopic era also revealed the dynamic nature of the galaxy. Proper motions, the actual movement of stars through space, could now be measured with increasing precision. This led to the discovery of stellar associations, moving groups, and streams of stars, providing crucial clues about the formation and evolution of our galaxy. Perhaps most importantly, the telescope era demonstrated that precision in astronomical measurement was not just about better instruments, but about understanding and controlling sources of error. Astronomers developed sophisticated techniques for calibrating their instruments, accounting for atmospheric effects, and handling observational uncertainties. These methodological advances were just as important as the technological ones in advancing the field of astrometry. We often think of scientific revolutions in terms of dramatic theoretical breakthroughs, but the telescopic era in astrometry shows us that sometimes the most profound advances come from our ability to measure things more precisely. Each improvement in precision revealed new aspects of the cosmic architecture, gradually transforming our view of the universe from a two-dimensional celestial sphere to the rich, three-dimensional realm we know today. The launch of the Hipparchus satellite by the European Space Agency in 1989 marked the beginning of a new chapter in the history of astrometry, one that would revolutionize our understanding of the cosmos. Named in honor of the ancient Greek astronomer Hipparchus, this space-based observatory represented humanity's first attempt to conduct high-precision astrometric measurements from above Earth's atmosphere. Consider for a moment the limitations that had plagued ground-based astronomers for centuries. Atmospheric turbulence distorting stellar images, weather conditions limiting observation times, and Earth's rotation restricting the duration of continuous measurements. Hipparchus changed all that. Floating in space, free from atmospheric interference, it could make observations with unprecedented precision, achieving accuracies of around 1 millisecond, about 1,000 times better than what was possible from Earth. During its operational lifetime of just under 4 years, Hipparchus accomplished what would have taken ground-based observatories centuries to achieve. It precisely measured the positions, distances, and proper motions of more than 100,000 stars, creating the most accurate stellar catalog ever produced at that time. The mission's impact was immediate and profound. Astronomers suddenly had access to precise parallax measurements for stars up to 1,000 light-years away, vastly expanding our three-dimensional view of the local galaxy. But Hipparchus was just the beginning. In 2013, ESA launched its successor, the Gaia Space Observatory, and this is where the story takes a truly extraordinary turn. If Hipparchus represented a revolution in astrometry, Gaia initiated nothing less than a cosmic renaissance. The numbers alone are staggering. While Hipparchus catalogued 100,000 stars, Gaia is observing more than 1 billion stars, measuring their positions, distances, proper motions, and brightnesses with extraordinary precision. To appreciate the leap forward that Gaia represents, consider its precision. It can measure stellar positions with an accuracy of up to 7 microarcseconds, roughly equivalent to measuring the width of a human hair from 1,000 kilometers away. This level of precision allows Gaia to detect minute wobbles in stellar positions that can reveal the presence of previously unknown planets orbiting distant stars. But Gaia's capabilities go far beyond just measuring stellar positions. The spacecraft is equipped with a billion-pixel camera and 2 telescopes that work together to create what amounts to a cosmic census of our galaxy. It measures not just where stars are, but how they're moving, how bright they are, what color they are, and even their temperature and composition. This wealth of data is allowing astronomers to create the first detailed three-dimensional map of our galaxy, complete with stellar motions that reveal the Milky Way's complex dynamics. The impact of Gaia's observations extends far beyond simple star cataloging. Its data has revolutionized our understanding of the Milky Way's structure and evolution. It has revealed previously unknown stellar streams, the remnants of ancient galaxies consumed by our own, and identified vast waves of stars moving through the galaxy's disk, possibly triggered by a long-ago collision with a dwarf galaxy. Gaia has even helped astronomers refine their measurements of the galaxy's mass and rotation curve, providing new insights into the distribution of dark matter. Perhaps most excitingly, Gaia is revealing the dynamic nature of our galaxy in unprecedented detail. By tracking the precise motions of billions of stars, it's showing us that the Milky Way is far from a static system. Instead, it's a dynamic, evolving structure, still bearing the scars of ancient collisions and actively responding to the gravitational influences of nearby galaxies. The space revolution in astrometry has also had profound implications for other areas of astronomy. The precise distance measurements provided by Hipparchus and Gaia have helped calibrate other cosmic distance indicators, improving our understanding of the universe's scale and expansion rate. The missions have identified countless variable stars, providing valuable data for understanding stellar evolution and cosmic distance measurements. As we look to the future, the legacy of this space-based astrometric revolution continues to unfold. Each data release from Gaia brings new discoveries and insights, from previously unknown stellar clusters to mysterious stellar streams and unexpected galactic structures. What began with Hipparchus counting stars by more than 2 millennia ago has evolved into a comprehensive survey of our galactic neighborhood, providing us with an unprecedented view of our cosmic home. This revolution in astrometric precision hasn't just improved our measurements, it has transformed our very conception of the galaxy we live in. We now see the Milky Way not as a static collection of stars, but as a dynamic, evolving system with a rich and complex history written in the motions of its stars. From Hipparcos to Gaia, the space age of astrometry has given us not just a map of the cosmos, but a window into its past and future. The journey of astrometry stands as one of humanity's most remarkable scientific achievements, spanning over 2 millennia of human ingenuity and determination. From Hipparchus's humble catalog of 850 stars to Gaia's unprecedented survey of over 1 billion celestial objects, this evolution represents far more than just an improvement in numbers. It tells the story of humanity's relentless quest to understand our place in the cosmos. Consider the extraordinary path we've traveled. In ancient Greece, armed with nothing but their naked eyes and basic measuring tools, astronomers could barely achieve accuracy within a degree when measuring stellar positions. Today, our space-based observatories can pinpoint stars with precision measured in microarcseconds, an improvement in accuracy of more than 1,000,000-fold. This progression isn't just about better technology, it's a testament to human curiosity and perseverance. Each era in astrometric history has built upon the achievements of those who came before. Hipparchus's methodical approach laid the groundwork for Tycho Brahe's revolutionary observational techniques. Brahe's unprecedented precision made possible Kepler's laws of planetary motion, which in turn influenced Newton's theory of universal gravitation. The invention of the telescope enabled Bessel to measure the first stellar parallax, finally proving that stars were distant suns and giving us our first true sense of cosmic scale. But perhaps what's most remarkable about this journey is how each advancement has revealed new layers of complexity in our universe. As our measurements became more precise, we discovered that the cosmos was far more dynamic and intricate than we had ever imagined. Stars that appeared fixed and unchanging to ancient observers were revealed to be in constant motion, participating in an elaborate cosmic dance choreographed by gravity. The seemingly simple questions of where stars are and how they move led us to profound discoveries about the structure and evolution of our galaxy. The modern era of space-based astrometry, from Hipparchos to Gaia, has transformed our understanding of the Milky Way from a static collection of stars into a living, breathing entity with its own biography written in the motions of its stellar constituents. We've discovered that our galaxy has cannibalized smaller galaxies, that it bears the scars of ancient collisions, and that it continues to evolve and change before our very eyes. This journey of discovery continues. Each new generation of instruments reveals previously unknown phenomena, poses new questions, and challenges our understanding of the cosmos. From measuring the positions of a few hundred stars to mapping the three-dimensional structure and dynamics of our entire galaxy, astrometry has expanded our cosmic perspective in ways that would have been unimaginable to its pioneers. Yet perhaps the most profound aspect of this journey is what it tells us about ourselves. The story of astrometry is a reminder of humanity's capacity for wonder, our ability to solve seemingly impossible problems, and our unwavering desire to understand our place in the universe. From the ancient astronomers who first attempted to map the heavens to the modern scientists analyzing data from space-based observatories, we have never stopped asking questions about our cosmic environment. As we look to the future, we can only imagine what new discoveries await us. The precision of our measurements continues to improve, our understanding of stellar physics grows more sophisticated, and our ability to process and analyze vast amounts of data becomes more powerful. Each advance brings us closer to answering fundamental questions about the nature of our galaxy, its history, and its future. If you found this journey through the history of astrometry as fascinating as we have, we invite you to continue exploring these cosmic mysteries with us. Join our community of universe explorers at Exploring the Universe, where we regularly share new discoveries, insights, and the continuing story of humanity's quest to understand the cosmos. Don't forget to share this video with others who might be inspired by this remarkable scientific journey, and subscribe to our channel to stay updated on the latest developments in our understanding of the universe. Remember, every time you look up at the night sky, you're participating in a tradition that stretches back to the dawn of civilization, the human desire to understand our place among the stars. The story of astrometry is, in many ways, the story of human curiosity, innovation, and perseverance, and it continues to unfold with each new generation of explorers and each new technological advance.